All right, welcome back, everybody. So again, today what we're doing is section 3.2, using algebraic methods to solve linear systems. So we just talked about solving a system is to find the intersection point, whether we find it graphically like we did in section 3.1. Today what we're going to talk about is solving algebraic methods, using algebraic methods to solve systems of equations. Now, we have three methods to do that. We have graphing, and then we're going to have substitution, and then we're going to have elimination, okay? Does that ring a bell if I say substitution and elimination? Is that kind of like, oh yeah, I remember vaguely what that is? No, I don't, sorry. All right, so let's go through what that is. Now, why do we have substitution and elimination? Well, if we didn't have our calculators to graph and find the intersection point, we would need to graph these things by hand. And what would happen if the solution came out to be something like this? What happens if it's at a middle point? What happens if it's like at a 0.7 comma 1 point something, right? Then our graphing by hand wouldn't really tell us what to do. So we have to come up with another method. We have this method called substitution. There's substitution and elimination. They don't rely on graphing to solve the system. We know what we're still looking for, right? The goal in the end is to find the intersection point by whatever means necessary. If we solve this by graphing, we can't really tell. We can kind of estimate where it's going to be, but we can't tell exactly. So let's take a look at how we solve by substitution. So basically, in general, to solve by substitution, we solve one of the equations for one of the variables and input that into the second equation, right? We solve one of the equations for one of the variables, and sometimes that's already done for us, and in those cases, life is good. But then you take that and you plug it into the other equation and solve for one of the variables. And once you get one of the variables, it's pretty easy to find the other. You just plug it into one of the equations, and there you have the other. Okay, so let's do this together here. 2y plus x is equal to 4. 2y plus x is equal to 4, and then 3x minus 4y is equal to 7. Okay, can anybody tell me what the easiest variable to solve for is? What's the easiest variable to solve for? X in the top one, right? X in the top one. Remember, I'm going to be using this notation where I'm going to name them like this is equation 1 and this is equation 2. So solving for x in equation 1 is going to be the easiest route to take. Why? Because it's by itself. It has no coefficient, right? It has no coefficient. To solve for x, all I need to do is take 2y plus x is equal to 4 and just subtract the 2y over to the other side. X is equal to 4 minus 2y. Right? We solve one of the equations for one of the variables, and then we input that into the other equation. Don't go back into the same one. It's always going to cancel out if you put it back in the same one. Right? If I put it back into equation 1, the one that I solved, that's no good. You don't want to do that. You want to take this x. If x is 4 minus 2y, I take that and I plug it right in for x into the second equation. Leave the coefficient that was there. Like this is a 3x minus 4y, right? So I'm going to take 3 times 4 minus 2y minus 4y is equal to 7. You guys follow me there? That's what substitution really is. We take one of the equations for one of the variables and we substitute that in. Like we remove it and in its place we write something that's equal, right? Okay, now I distribute in. We solve this. 12 minus 6y minus 4y is 7. We combine like terms here. We get 10 minus 10y. Be careful with that. Don't make that a negative 2. Negative 6 minus 4 is negative 10. We subtract the 12 over to the other side. Negative 10y is equal to negative 5. And then we divide by negative 10. Y is 1/2. Y is 1/2. See, this is a case where, because this is a decimal, it would not have come out to a nice clean point on our graph. We wouldn't have been able to tell by graphing. So now at this point, once you have your y value, you can start to make your final answer, something comma 1/2, right? Don't lose sight of the end goal. The end goal is to find the intersection point, the location. I can plug it back into either one of my two equations, but in my opinion, it's going to be easiest to plug it back into equation 1, because x doesn't have a coefficient again, right? So we go back into equation 1, plugging in y as 1/2. 2 times 1/2 is 1. So x is 3. Remember, please don't give me x equals 3 and y equals 1/2. Those are lines, right? We learned last chapter that x equals is a vertical line, y equals is a horizontal line. So don't give me x equals, y equals. Give me a coordinate, 3, 1/2. Again, the location of the intersection point. That's what we're looking for there. Does that ring a bell? Like, oh yeah, I remember this now. Okay, let's do this one here together. Okay, what's the easiest route to take? What's the easiest route to take? Solving for what equation, or what variable in which equation?
Equation 2, solve for y.
Good, equation 2, solve for y. Because again, it doesn't have a coefficient, right? So here's equation 1, here's equation 2. We got 7x plus y is equal to -4. We subtract over the 7x. Y is equal to -4 minus 7x. You don't need to worry about putting it in slope-intercept form, because we're not graphing. Like, you don't need to put the x first. So I've input that into equation 2. Remember this, or sorry, I'm using equation 2. I input it back into equation 1. I put it back into here, right? Goes right there. So this becomes 56x plus 8 times -4 minus 7x is equal to -32. Again, I remove the y value. I don't remove the 8. The 8 stays. Now watch what's going to happen here. I distribute in the 8. I get 56x. That should be a minus 32. Minus 56x is equal to -32. What happens to my x coordinate? What happens to my x variables, excuse me? All right, cancel. I end up with -32 is equal to -32. What's the answer when you have something like that? Exactly, all real numbers. So what can you tell me about those two lines? They're coinciding. Good. They're coinciding. The lines are they graph to be the same exact thing. There's an infinite amount of solutions. We would classify that as consistent dependent. Remember? Consistent means it has a solution. Dependent means it has the same slope and y-intercept, meaning it's the same line. Okay. So if you get an all real numbers type situation, that understand what that means in terms of the system. You know, because this was a true statement, we'd get an all real numbers. If this was a false statement, we'd get a no solutions. What would be the system if I got a no solutions? What would be the lines if I got a no solutions? Parallel lines. Parallel lines. Inconsistent system. Right. Okay, so that's substitution. Let's talk about elimination. Flip over your guided notes here. Let's talk about elimination. Okay, you can also solve systems of equations with the elimination method. I know you guys like to do substitution more than elimination. I just, from teaching this a long time, I know that you guys like to do substitution more than elimination. I don't know. I like elimination better than substitution. I don't know why. I just do. I think it's cleaner sometimes. Once you get it set up correctly, I guess I should say that. Once you get it set up correctly. Basically, with elimination, you get rid of one of the variables. You eliminate one of the variables by adding or subtracting the equations. I never like to subtract the equations. I always like to add. I'll multiply by a negative if I have to, so I can add. Okay? You may have to multiply one or both of the equations by a number to create variable terms that can be eliminated. Do I need to multiply anything here with my example? This is set up for elimination. This is already set up for elimination. I don't need to multiply anything. And I know because of this right here. Everybody see that? Not only is it the same value, 2y, but one's positive and one's negative. That's a perfect scenario. Okay, one's positive and one's negative. And they are the same value. So all I need to do is just add these two equations vertically. That's it. I just don't ignore the stuff on the right there. We add these two equations vertically. 3x plus 4x is 7x. The positive 2y and the negative 2y cancel each other out. They eliminate. Right? That's where it gets its name, elimination. They eliminate because they cancel each other out. 4 and a negative 18 gets us negative 14. And then it gives us this nice, simple one-step equation to solve, right? We divide by 7, we get x is equal to negative 2. At that point, it's the same thing as substitution. Once you have one of the variables, once you get x equals negative 2, you can plug it back into either one and figure out what the y value should be. So it looks like we go back into equation 1, plugging it back into equation 1. 3 times negative 2 plus 2y is 4. So I would add over the 6 and then divide by 2. I get y is equal to 5. Again, don't lose sight of the end goal. The end goal is to try to find the location of the intersection point. So in this case, it's negative 2 comma 5. Negative 2 comma 5. Make sense? Again, this one was set up for elimination because I have both positive and negative of the same value. If that's not happening, we have to make that happen by multiplying one or both of the equations. For example, here. This is example 2, letter A. I want to use elimination to solve the system of equations. Is this set up for elimination yet? No. The first thing that you should always check is to make sure that everything's lined up. I've got x's, I've got y's, I've got my constants. Good. These are both what's known as standard form. ax plus by equals c, right? Okay. At this point, we can choose whichever variable we want to eliminate. In my opinion, they're both just as easy to eliminate with. But the goal is to try to get them to the same number. Say I wanted to eliminate with the x's. What number am I going to try to get them both to? 6. Say I wanted to eliminate with the y's. What number am I going to try to get them both to? 15. What number is that? What do we call that number? Do we know? What do we call that number? Least common multiple. The least common multiple. If these were in denominators, we would call it the least common denominator, right? But it's the least common multiple of the two numbers. That's what you're looking to get it to. Right? You're looking for the least common multiple of the coefficients, and that's what you're trying to get it to. Okay, so if I wanted to get this to 6, what would I multiply 3 by to get to 6? Obviously 2, right? Now, here's the deal. To be able to add down, I would like them to be opposite signs. Right? To be able to add instead of subtract, I would like to have them be opposite signs. So instead of multiplying by a positive 3 on the bottom, I'm just going to multiply by a negative 3, and then it'll work itself out in the end. I can just add down rather than having to worry about any subtraction business. Okay, so that means that this equation 1 turns into 6x plus 10y is equal to negative 32. I'll tell you what, one of the main mistakes I always see is people not distributing into everything. Like you'll say 6x plus 10y is equal to negative 16 and forget to multiply by the constant in the end. Don't do that. Don't do that to yourself. Okay. Negative 3 in. Negative 3 times 2x is a negative 6x. Negative 3 times 3y is a negative 9y. Negative 3 times negative 9 is a positive 27. See, at this point, it's set up for elimination. I can add down now. It eliminates with the x's. Look at that. Fancy enough. I just get a y. That's nice. And then it's negative 5. Wow, that was convenient. I don't even have to divide by anything. Y is negative 5. So let's plug it in and solve for x. 3x plus 5 times, I'm just going back into equation 1. 3x plus 5 times negative 5 is equal to negative 16. We solve for x here. 3x minus 25 is negative 16. I add the 25 over to the other side. I believe that's a 9. And then we divide by 3. X is 3. So the coordinate is 3 comma negative 5. Make sense? Would we all agree that I would definitely not, if I had my choice, I wouldn't really want to do substitution here? I mean, think about solving for any one of those variables. Like if I wanted to solve for y here, I would have to subtract the 2x and then divide everything by 3. Ah, that's messy fractions. No thanks. If I wanted to divide, or if I wanted to solve for y on the top, I'd have to subtract the 3x and divide by 5. No thanks. Then input that into the messy fractions. I know it all works out in the end, but geez, no thanks. That's just nasty. All right, so what's going to happen if I've got like parallel lines or coinciding lines with elimination? The same type of thing happens with substitution where the variables all will cancel out. What do I have to pay attention to right off the bat, though? The order. Look at that. I've got 3x plus y is equal to 1. 2y plus 6x is equal to negative 18. So I'm going to manipulate this just a little bit. The top equation will stay. Already in standard form, the bottom equation needs to become 6x plus 2y is equal to negative 18. Make sure everything's lined up. Okay, say I wanted to eliminate with the x's. Say I wanted to eliminate with the x's. What's the first thing that I would need to do to, or what would I need to multiply the first equation by? What do I need to multiply the top equation by? What's that? 2? I would say negative 2, right? I would say negative 2, because look, I want to get it to be a 6. So all I need to do is multiply by negative 2 to make it be a negative 6, and then I can just add down. So this becomes a negative 6x minus 2y is negative 2. And this becomes, stays the same, 6x plus 2y is equal to negative 18. Okay, now I can add down. We good? Now I can add down, right? I could just take, well, that cancels. That cancels. I get a 0 on the left side. Is that a true statement? No. When you get a false statement, what's my answer? No solutions. There are no solutions. That means that these lines are parallel, right? If I'm thinking about the solutions of where the lines will cross, and I say there are no solutions, that means the lines will not cross, which is the definition of parallel lines. Okay. Questions on solving substitution or elimination? No, we good there? Okay. Now, for the sake of keeping track of groups and everything like that, and I've got to know who's in what group and everything, I know don't throw things at me. I assigned you groups. Okay. Sorry, you don't get to pick your groups, but so I just assigned you groups. I just kind of went through and